Hi, I'm Shuli Rafgal from Bar-Ilan University, and together with my co-author Carlo Meloni from the University of Zurich, I will present our work on neural proto-word reconstruction. This is joint work with Carlo and my advisor Yoav Goldberg. We know that languages change over time. These changes can be in the syntax of the language, the meaning of words, and finally in the phonology, or sound system. In this work, we focus on the latter change, sound change. We explore the ability of neural networks to learn the regularities of sound change. Historical linguists deal with the reconstruction of ancestral languages called proto-languages on the basis of words they observe in their daughter languages. To do so, they identify a set of cognate words, that is, words sharing a common ancestor. By their comparison, they identify regularities in the sound change, which can be used to reconstruct the form of the proto-word. As an example, consider the similarity between the different words in the Romance languages for the word sky, presented here. We present the IPA form, the form that encodes how the word sounds, in square brackets. Let's focus on the first sound of these words. There is a great deal of similarity between the different forms, but some differences too. For instance, the Sardinian word starts with ke, while the Italian one starts with che. We observe the same correspondence in many different cognate sets. This suggests that there exists a regular correspondence between these sounds. Using their phonological knowledge, linguists can reconstruct the original sound in the ancestral word from which all the daughter words were derived. Here this is the sound ke. By using the same process, linguists can reconstruct all the sounds of the original words, and by that they can reconstruct the lexicon of the ancestral language. Here the ancestor word is kailum. In this work we ask, can this process be approximated with a neural model? That is, can we have a neural model that is trained to reconstruct the Latin form based on a set of cognates in the daughter languages? This is not an easy task. Word reconstruction relies on several intermediate tasks, such as finding a set of cognates, identifying the sound changes, and employing the phonological knowledge in order to reconstruct the original sound. We focus on the Romance languages since they are thoroughly researched, and the rules of phonological change are already pretty much mapped. This allows us to test whether the model learns the same rules historical linguists have identified. This is not possible in other NLP tasks, parsing for example, where linguists still argue about the right theoretical explanation for various phenomena. We cast the problem as a seek-to-seek problem. The model gets the cognates as an input and outputs the Latin form. We perform an extensive analysis of the model's performance, studying whether it learns the regularities of the sound change, whether some sound changes are more difficult than others, and whether the model learns a meaningful representation for phonemes. To do so, we first construct an extensive etymological dataset of the Romance languages, then we train a simple baseline model over this dataset, and finally we inspect the model's generalizations. Now, high-quality online datasets for the Romance languages are scarce, and existing ones suffer from several problems. They include false cognates, truncated forms, non-existent words, and often have a mismatch between the part of speech of the cognate and the ancestor. We present a new dataset. We based it on the dataset presented by Chubano and Dino on 2014. We performed an extensive validation and normalization of this dataset, fixing many of the above-mentioned problems. In addition, we significantly extended it with dictionary scraping. We include cognate sets in 5 Romance languages: Spanish, Italian, Portuguese, French, and Romanian, together with their Latin ancestor. This results in a dataset that contains over 8,000 entries and over 40,000 distinct words across the different languages. We will shortly describe some of the main standardization procedures we have employed. We have normalized all Latin nouns to their accusative forms. We have converted all Romanian nouns to their indefinite nominative accusative form, and finally we have converted all verbs in all languages to their indefinite forms. Now, Latin vowels are divided into long and short vowels. They differ in the duration of their pronunciation. This difference is seldom represented in existing datasets, although it is relevant for the evolution of vowels in daughter languages. Therefore, we added vowel length to all Latin entries. Finally, the dataset was automatically transcribed to IPA form, which accurately represents the pronunciation of words. It is interesting to compare the signal in the orthographic and IPA datasets since orthography is more conservative in nature and may help the model in reconstructing the original form. We use a character-based gyro network as the encoder-decoder. It generates the Latin form one character at a time. We represent the input as the sum of character embeddings and learned language identity embeddings. In our experiments, we tested the reconstruction of both the orthographic and the IPA form. As vowel length was extremely difficult to reconstruct, we also tested performance without it. As an evaluation measure, we use edit distance, the number of one-character edits to transition from the gold to the generated form. For instance, consider the predicted form lodare on the left and the Latin gold laudare on the right. To transform from the predicted to the gold, we first change the O sound to A, and then we add U, resulting in an edit distance of 2. Okay, so far I've described the motivation and the experimental setup. I will now let Carlo describe the experimental results and analysis.
Thank you, Shauli. Now we will discuss the results of the reconstruction task. In the rows, we see the two settings, orthographic versus IPA. In the column, we first see the percentage of cases where the edit distance was at most k for k between 0 and 4. We also measure average edit distance and normalized average distance, that is, edit distance per character. As we can see, the network performed poorly on the task with only 42% full reconstruction for the orthographic dataset and 47% for the IPA dataset. We hypothesized that this difference stems from a single factor, vowel length, since this feature was lost in all the daughter languages. When we neutralized vowel length, we see an improvement in both datasets, although the improvement is much more significant in the orthographic dataset. We can explain this by the fact that even if we remove explicit vowel length, it is still present in the IPA form via the tense lax contrast. We will not get into the details, but this is a phonological property implicitly influenced from length. Thus, we also evaluate on the IPA dataset without this distinction. Here, as we can see, without the latter contrast, the performance over the IPA dataset is similar to the performance over the orthographic one. Inspecting the model's reconstructions, we observed that the errors were not arbitrary, but rather fall into several well-defined error categories that are reflected in different sound change processes. By inspecting the number of errors from each category, we can assess which categories are more difficult for the model. Here we list all the categories, and we are going to discuss some of them now. First, the network found challenging to reconstruct correctly I and mid vowels. The model often confused between the two. For example, the network reconstructed pescarium with a mid vowel instead of piscarium with a I vowel. Several consonant sequences were simplified or underwent assimilation in the evolution of the daughter languages, and the network often wrongly reconstructed them. We can see an example of a wrongly reconstructed consonant in vessare instead of vexare, and a wrongly reconstructed cluster in reationem instead of reactionem. Moreover, we found that the reconstruction of vowels was more challenging for the model than the reconstruction of consonants. Those errors, too, can be divided into several categories, as it's possible to see from the picture. As said, the main problematic issue was the reconstruction of vowel length, reflected in the tense lax error category. The errors analysis also revealed that the network was able to generalize some phonological patterns of Latin. Latin nasals tended to assimilate to the place of articulation of the adjacent consonant, deriving clusters such as nk, mp, and nt. When the model deleted, for example, the velar stop k in the word distinctum, the network reconstructs an alveolar nasal matching the following consonant, distinctum. Similarly, by deleting the bilabial plosive p in the word redemptionem, the nasal consonant changes to an alveolar one, redemptionem. We already mentioned that the sound changes between Latin and the Romance languages are systematic. We can formulate them as a set of phonological rules, such as Latin ski transforms to Spanish thi. We wanted to find out whether the network was able to learn those rules. In order to do so, we collected 33 of such rules and created a synthetic test set containing syllable examples, each focusing on a different phonological change. For example, the rule cited in the previous slide would be represented in this way. The Latin etymological sounds are found to the left, while the sounds in the daughter languages are found to the right. The model was supposed to reconstruct the original Latin syllable based on the daughter languages. The correct reconstruction of a syllable was taken as evidence that the model learned the relevant phonological rule. The network correctly predicted 22 out of the 33 phonological rules, that is about 67% of the changes. These results are compatible with the results on the main reconstruction experiment. In general, the model correctly reconstructed phonemes retained with little or no changes in all languages, or that change in a predictable way in each one of the daughter languages. In contrast, the changes that were less regular and more influenced by the phonological environment were opaque and harder to learn. Another question that we tested is whether the training on the task of proto-word reconstruction implicitly encouraged the model to acquire phonologically meaningful representation. We performed hierarchical clustering on the characters embedding vectors and found that phonologically similar phonemes are grouped together in hierarchical clustering. We performed such clustering for all the languages in our dataset, but we will focus here specifically on the French one. First, it is possible to see that the main meaningful division is between consonants and vowels, which are grouped separately. We can find other generalization as well. Pairs of voiced and voiceless consonants that are grouped together, sibilants that share similar representations, glides that are set apart from the other consonants, and even allophones that are characterized under the same branch. So, in conclusion, for performing the main task of proto-word reconstruction, we created a new historical dataset for Romance languages. We showed that our model was able to carry out this task and that neural sequence models are a good baseline for it. And finally, the extensive error analysis revealed that some phonological processes are more difficult to reconstruct than others, chiefly vowel length. Nonetheless, it seems that the model was able to learn abstract rules of sound change, and that the task encouraged the model to learn phonologically meaningful representation for the phonemes. There is still a lot to do on the subject. First, the main desideratum should be to create an unsupervised reconstruction model, which would reflect more accurately the comparative method as applied by historical linguists. Although it seems that the model indeed learned rules of sound change, you would want to assess it also by other means. And finally, the same process should be implemented also on other languages. Thank you so much for your attention. You can find more details about our research in the paper.